Okay, ladies. All right, we're going to talk about a few things. The first thing we're going to talk about is something called percent composition. Now, in this case, we're referring to percent composition by mass of an element in a compound. So let's look at the first question, all right? What would be the percent composition of hydrogen in water? So if we were to figure out, imagine we could split water and weigh the amount of hydrogen and oxygen, what would be the percentage contributed by hydrogen in this case? So always start with a formula, which is what? Water would be H2O, right? H2O. So you could see in the formula that there's 2 hydrogen and there's 1 oxygen, right? Now, the molar mass of hydrogen is what? What's the molar mass of hydrogen? Is it 1.01? Okay. So we have 2 of them. So that would mean that we have a total of 2.02 for hydrogen. Right? Because remember the mole. So if we had 1 mole of water, right? Then remember 1 mole of water would be 2 hydrogen atoms plus 1 oxygen atom. What would be, now that looks like a 10, but that's actually 1 oxygen. So what's 1 oxygen? 16.0? So that would be 1 of them. So that's 16. So the molar mass of water then should be what? Should be 18.02 grams per mole. So what would be the percent due to hydrogen? Well, that would just simply be the proportion of hydrogen. In this case, it would be what? 2.02 over the mass of water, the molar mass of water, times 100%. Very, very easy stuff. So what would that be? It's about 1/9. It should be close to 11%. Is it? 11.2? Well, let's have rounded off to 3 significant digits. So 11.2%. Which means then the mass of oxygen would have to be 89.8%. How's that? Easy so far, right? Okay. How about we do the same thing but with maybe a bigger compound. So like, for example, what would be the percent of oxygen in calcium phosphate? So start with the formula. What's calcium phosphate? Ca3PO4 2. Okay? So we can see by our formula that we have 3 calcium. So we have 3 calcium. We have 2 phosphorus, and we have 8 oxygen, right? Okay, so let's work out each one. So 3 calcium, so that would be 3 times, what's the molar mass of calcium? 40.08. Okay, phosphorus? 30.97. And then 8 oxygen. 16.00. So now we add that all up. So this is good review for how to do molar mass, right? So 3 times 40.08 plus 2 times 30.97 plus 8 times 16.00. 310.18. Okay? Now, here's the thing. That's the molar mass of calcium phosphate. So the percent of oxygen then would be, well, oxygen is 8 times 16, which is what? What's 8 times 16? Yeah. So it'd be 128 over 310 times 100%. So what's the percent of oxygen? 41%. Okay. 41.3. Well, we have, we can do 4 significant digits. So, 2.27? Okay. So, about 41% oxygen, right? Easy so far, right? Percent composition? Okay. So far. Now, you guys have, so you can see here that you have, examples where you have a name. Like, one of the skills you've learned is give you a name, you give me the formula, right? Okay. That's called a molecular formula. So what would be the molecular formula for table salt? Na what? NaCl. What would it be for glucose? Okay, so the molecular formula for glucose is C6. Well, what's going on here? Sorry. Why is it doing that? Okay. Yeah, don't know what happened there. Okay. So the molecular form for glucose is, let me just erase that. It's C6H12O6, right? Now, the empirical formula just refers to the formula when you can reduce things to their lowest ratio. It's not the actual formula, it's just the ratio of the atoms in the formula. So in other words, for glucose, the empirical formula would be CH2O, because if you look, what could we divide everything by? By 6, right? So that would mean that so the empirical formula is just the ratio of the atoms in the formula. It's not the formula. It's just a ratio, okay? So it just says that for every 1 carbon, we have 2 hydrogen, and we have 1 oxygen. So for example, in hydrogen peroxide would be so H2O2. So the empirical formula would be HO, which means there's 1 hydrogen for every 1 oxygen. Easy so far, right? Okay, so let's look at this. What would be the empirical formula for a compound that is 40% carbon, 53% oxygen, and 7% hydrogen? Okay? So this is what I would do if I were you. I would think of it in terms of moles, right? Moles. So let's look at carbon. Actually, let's imagine this. Let's imagine we had 100 grams of this substance. 100 grams, okay? So if I had 100 grams of this compound, then I would know that about 40 grams would be what? Carbon. 53 grams would be oxygen. And 7 grams would be hydrogen, correct? Okay. Now, this is what I'm going to think of this in terms of moles. Alright? Let's look at carbon. So, I'm going to look at carbon, and I'm going to ask a very simple question. How many moles does 40 grams represent? So, number of moles is what? Number of moles is the mass over the molar mass. Remember that from previous lesson? So that would be 40 grams over, what's the molar mass of carbon? I'm just going to round it off, okay? I'm just going to round everything off here. 12 grams per mole. Okay? So what would 40 grams represent in terms of moles? 3.33? Okay. 3.33 moles. Now I'm going to do the exact same thing for oxygen, but I'm just going to just use the molar mass of O, not O2. Okay? I'm going to use O. Remember, the molar mass of O2 is 32, but the molar mass of O is just 16. Very good. So how many moles is 53 grams? Well, that would be 53 over 16. And what would that be? 3.33? Okay. But look, right away I can tell that the number of carbon and number of oxygen atoms is in a 1-to-1 ratio. You understand that? That for every one carbon of for every one carbon atom, I'm going to have one oxygen atom. Just because I can see that the number of moles is exactly the same between the two. Now let's look at hydrogen. What about hydrogen? So what would be the number of moles of hydrogen? Okay, well, it's 7 grams over 1. So, what's that? Well, 7. Now, again, these numbers are rounded off. Okay, they're rounded off, but 7 is almost twice as big as 3.33. In fact, 7 would be twice as big as 3.5. So the ratio to me is if I divide everything by 3.3. So I have carbon, I have oxygen, and I have hydrogen. And carbon is 3.3, oxygen is 3.3, and hydrogen is 7. What I can do is a formula does not have, it doesn't have integers in it, it has whole numbers. So I'm going to round this off. So what I'm going to do is I'm going to divide everything by 3.3. If I divide everything by 3.3, I'm going to get 1 here, I'm going to get 1 here, and I'm going to get 2.12, which is very close to 2. So to me, it looks like the empirical formula would be, now, when you're doing anything with carbon, oxygen, and hydrogen, you should write the carbon first, the hydrogen second, and the oxygen third. So the empirical formula then would be, I'll just slide it up here, would be CH2O, which would be the same as the empirical formula for glucose. Okay? Alright? Now, that's the empirical formula, but what if we wanted to know the actual molecular formula? Because the thing about the empirical formula is we could have a carbohydrate, because that's what that is C3H6O3. You could have one that is C5H10O5. You could have one that is C6H12O6. But you notice the empirical formula is always 1, 2, 1, right? It's 1 carbon, 2 hydrogen, 1 oxygen. So the empirical formula doesn't tell you the molecular formula. We need one more piece of information. So what we need is the actual molar mass. Okay, we need the molar mass. So let's imagine that in scenario 1, the molar mass is 90 grams for 1 mole. Okay? Now, we go to our empirical formula, right? Our empirical formula is what? CH2O. What would be the molar mass of CH2O? So how would we do that? So we have 1 carbon, 2 hydrogen, 1 oxygen. And carbon has a mass of about 12. Hydrogen has a mass of 1. And oxygen is 16. So that would be 12, 2, 16. So what does that add up to? 30? 30 grams per mole. Right? That's the molar mass of CH2O. Now, if we have a substance, so for number 1, that's 90 grams per mole, then that would be 3 times this value, correct? This is 30. So CH2O would be 30. 90 is exactly 3 times that value. So then if the empirical formula is CH2O, then the molecular formula must be C3H6O6. Right? I was just seeing if you're paying attention. Okay? So C3H6O3. Easy so far? The math is not difficult. It's the reasoning that might be a little bit tricky. So then, what should the molecular formula for 180 be? Well, 180 is exactly how many times bigger than 30? So 6 times. So then it stands to reason that then it should be C6H12O6. Okay? Alright, ladies? What do you think? You want me to pause the video and let you finish copying this down? Or just move on? Cha-cha? What do you want to do? Move on? Alright. So we've looked at percent composition, we've looked at empirical and molecular formula. Now, let's go back to percent composition and see if we can use that to figure out formula, right? So, what was the formula for Epsom salt again? MgSO4 times 7H2O. Okay. All right. Now and the molar mass we've already worked out a few times. So what's the molar mass of 200 and what? 19 is it? Okay. All right. So we know that the molar mass of magnesium sulfate pentahydrate, because we've worked with it, is about 246 grams per mole, right? What then would be the amount of water that would represent its mass percent? So that percent of water then would have to be, if we had 1 mole, would have to be something over 246. Now, 7 molecules of water, what would be the mass of 1 mole of water? What was it again? It was about 18? Yeah. It was about 18, right? So what would 7 be? So so 7 moles of H2O would be what? It would be 7 times 18 point, what did we work out? 18.02, was it?
Yeah.
So what would that be? What would 7 moles of water represent in terms of its mass? 126.14. So the percent then of water would be 126.14 over 246.47. What would that represent? 51%. Let's round it off to 51%, which then means that the percent mass of the sulfate would have to be what? 49%. Because they have to add up to 100%, right? So in your Epsom salt, you have 2 things. You have your magnesium sulfate and you have your water. The water is 51%, so the magnesium sulfate must be 49%. Does that make sense? Okay. In your next lab, you're going to be given an unknown hydrate. And so hydrate is a compound with water attached to it, and you're going to have to figure out how many water molecules are in your substance. Now, because we already know what magnesium sulfate heptahydrate is, because we've worked with it, right? We know it's 7 molecules of water. But how would you figure out the number of water molecules if you didn't know the formula? Okay, so I'm going to show you an example. So let's imagine that you didn't know the formula for magnesium sulfate heptahydrate. So imagine you didn't know that. You knew what magnesium sulfate was. You knew that there's water, but you didn't know how many water molecules. So you would look at it in terms of like something like this. You would say, okay, I have magnesium sulfate, and I know there's water attached to it, but I don't know how much water. So I'm going to leave it as an X. I'm going to leave it as an X. I'm going to leave that as an, you don't want X as a variable? That's okay. So imagine we don't know what water is. We don't know how many water molecules. We're going to try to figure out doing an experiment. Okay? So you're going to do something like this. You're going to take a sample of your substance. In this case, it will be Epsom salt. So imagine we took 10.0 grams of Epsom salt. Okay? Now, imagine we heated it. And we heated it, and this is what you're going to do. We heated it. What do you think would happen to the Epsom salt? We heated it. What should happen? Considering the fact that water is attached to it, what should you start to see? Why? Why would the mass decrease? Very good. So if we heat this, the mass will reduce, right? You're going to lose mass because the water is going to evaporate. Imagine that you did this with 100% efficiency, which means all of the water evaporated out. Okay, imagine all of the water evaporated out. Now, we know that the water represents what percent? 51%, right? 51% of 10 grams would be what? Right? 51% would be 5.1 grams. So if you took your Epsom salt and you heated it, assuming that it was 100% efficient, all the water was removed, what would the Epsom salt's mass be after you were done heating it? Well, it would be 10 minus 5.1. Oops, 5.1. And that would mean that the Epsom salt would have a mass of about 4.9 grams, correct? And this is what you're going to do. You're going to take an unknown hydrate, you're going to heat it, and you'll notice that the mass will drop. The mass that you lose is the mass due to what? The water evaporating. Does that make sense? Okay. Now, here's what we know. 4.9 grams equals the mass of the what? What won't evaporate? Magnesium sulfate. Very good. Correct? Okay. We know the 5.1 grams is the mass of the water. So far, so good? Okay. Now, here's what we're going to do. Again, think in terms of moles. Okay? Think in terms of moles. Right? What does 4.9 grams of magnesium sulfate represent in terms of moles? So how would you do that? How would you do that? How would you figure out the number of moles that 4.9 grams represents? Yeah, Nora? N equals mass over molar mass, so it's 4.9 over, now what's the molar mass of magnesium sulfate? So you could work it out, or we could remember that magnesium sulfate is 49% of Epsom salt, and the Epsom salt's molar mass is 246.47. So 49% of that should be your molar mass for magnesium sulfate. So what would that be? Sorry, what was that? 100 and 120 point. So we'll just round it up to 8. So how many moles is that? How many moles would that represent? How many moles does that represent? 0.040 moles. Hold on, just don't worry about it. Then we're going to leave it at this, okay? Now, 5.1 grams is the water, right? How many moles does that represent? Well, it's the amount of water, 5.1 grams, over the molar mass of the water, which was about 18.02 grams per mole. So how many moles would 5.1 grams represent? 0.28 moles. Okay? So, we have 4.9 grams of magnesium sulfate, which is actually 0.040 moles. And we have 5.1 grams of water, which is 0.28 moles. Again, what's the formula for Epsom salt? MgSO4 times, no, hold on, we don't know what, imagine we don't know what the water is. We're trying to figure that out, okay? But now we're going to write down what we know. We know that the magnesium sulfate is 0.040 moles and that the water is 0.28, okay? Now, how can I make this 1? Well, how do I make 0.0401? I divide it by 0.040, and that gives me 1. But whatever I do to one side, do to the other side. So I divide this side by 0.040, and I get 7. And that's how you figure out the ratio between the amount of water and the compound that the water is attached to. Ladies, those are all the skills that, the knowledge that you need for chapter 6, okay? Percent composition, empirical formula, molecular formula, how to figure out the formula of a hydrate. It's all basically, remember, you got to use the mole. It's very important that you use the concept of the mole to figure this stuff out. Ladies, that is it. The